Hello students, welcome to EPG Pathshala. I am Dr. Savita Sharma from University of Delhi. Today we are going to discuss about the module Mechanical Properties Part 5 from the paper Electronic, Magnetic and Optical Properties of Materials. So students, let us see what we are going to learn in this module. We are going to study about the creep, like what is the creep. Then next we will study about the types of creep. What are the different types in which creep exists. Then we are going to study about the factors affecting the creep. Then we will learn about the mechanism of creep. Then we will study about the creep fracture. And in the end, we will study about the creep test. So to begin with, let us have a brief introduction of the mechanisms or the methods by which a material can fail. If failure is considered as change in desired performance, which could involve changes in properties and shape, then failure can occur by many mechanisms. Many mechanisms by which a failure occurs has been tabulated below in the given figure. So we can see the broad category and then we'll see the subcategories of these mechanisms. The first mechanism or method by which a material can fail is the elastic deformation. So the first reason for the failure of a material is elastic deformation. The second factor is the plastic deformation. We have already studied about the elasticity and plasticity in our earlier modules. So now the plastic deformation is further divided into two subunits or the two sub-methods by which a material can fail. The number one is the twining and the second one is the slip. So students, if you remember, we have learned about the twining and the slip in our earlier lesson. The third method by which a material fails is the fracture. Then the fourth method is the fatigue. The fifth method is creep. We have studied about the fracture, fatigue and creep in our last module. In this module, we'll focus on the creep, the methods of creep, the types of creep and then the creep test. The fifth method for letting a material to fail is the microstructural changes. If we can somehow bring the microstructural changes in a material, then that material will fail. The methods by which we can bring those microstructural changes are twining. The next change is the phase transformation. Then the third change will be its grain growth. If somehow we affect the growth of the grains of a material, then a material can fail. The fourth one is the particle coarsening. So by changing the microstructure of a material, by these four methods, we can cause a material to fail. Then the next broad category of the method or mechanism by which a material fails is the chemical or the electrochemical degradation. Meaning that if we degrade a material chemically or electrochemically, it will fail. The two sub-methods under this category are corrosion and oxidation. I hope students you know about the corrosion and oxidation, and we have also learnt about them in our earlier module. Then the last method or the mechanism by which a material can fail is the physical degradation. which is quite obvious that if we have the chemical degradation, then obviously we must be having a physical degradation as well for a material to fail. Now, the methods under the physical degradation are wearing and erosion. You know very well wear and tear, and then the erosion. So these are the major category of the methods or the mechanisms by which a material fail, and few of these methods have the subcategories which leads to these methods by which a material fails. The topic is creep. Permanent deformation of a material under constant load or constant stress as a function of time is creep. Normally, increased plastic deformation takes place with increasing load or stress. In creep, plastic strain increases at constant load or stress. Usually appreciable only at temperature greater than 0.4 Tm, that is the high temperature phenomena, creep occurs. Mechanism of creep in crystalline materials is different from that in amorphous materials. Amorphous materials can creep by flow. At temperatures where creep is appreciable, various other material processes may also be active. For example, recrystallization, precipitate coarsening, oxidation, etc., etc., as considered before. Creep experiments are done either at constant load or constant stress. The following figure shows the graph between creep strain and loading time. This is the creep curve at constant temperature and stress. This curve is divided into three regions. Region 1, that is between the point A and point B, shows the transient creep stage. The second region, which is between the point B and C, is the steady stage creep stage. The third one is the part of the curve from point C to point D, which is the third region, called as fracture stage. The distinguishability of these three stages strongly depends on T and sigma. That is, it strongly depends on stress and temperature. Now let us study about the various stages of creep. The first stage is when the creep rate decreases with time. That is, the effect of work hardening is more than recovery. The second stage of creep is the stage of minimum creep rate, which is almost constant. Work hardening and recovery are balanced. Then the third stage includes absent or delayed very much in constant stress tests. In this stage, necking of specimen starts and the specimen failure processes sets in. Now let us see the effect of stress. Here we can see the two diagrams or the two figures which represents the curve between the stress and epsilon, and the next curve represents the plotting of the strain versus temperature. So the first curve is versus stress versus strain, and the other curve is the strain versus temperature. We can easily see the 3 points which are denoted by epsilon naught prime, and epsilon naught double prime in the first figure. In the second part of the figure, we can see that in the initial regions of the curve, epsilon naught is increasing, and then further on with the curve, with each curve, like from the first curve to the third curve, the stress is increasing. Below that, there is a constant epsilon naught. Now let us discuss the effect of temperature. Here we can see a figure consisting of two parts. The part A shows a plot between the stress and strain, and these are the three curves at different temperatures. So there first is the stress and strain curve at some particular temperature, then the temperature is increased, and then again the temperature is increased, and there is a third curve. So we can see that as E is decreasing, as the temperature is increasing, and the point at which it cuts the axis, a particular axis, that are called as the epsilon naught for the first curve, epsilon naught prime for the second curve, and epsilon naught double prime for the third curve. Then in the second part of the figure, we see the graph between strain and temperature, and we observe that the epsilon naught increases with the increasing temperature. That is, for the first curve there is some value of epsilon naught, then for the second curve, when the temperature is increased, the value of epsilon naught is also increased. So we conclude that as there is a decrease in E with temperature is usually small, the epsilon naught increase is also small. Now students, let us classify the creep, or let us study the types of creep depending on the temperature. So the first classification of the creep is the logarithmic creep. At a low temperature, the creep rate usually decreases with time, and one obtains a logarithmic creep curve. So the first classification depending on the temperature is logarithmic creep, which is at the lower temperature. The second category is the recovery creep, in which at higher temperatures in the range of 0.5 and 0.7 of Tm into K, the influence of work hardening is weakened, and there is a possibility of mechanical recovery. As a result, the creep rate does not decreases rapidly as at low temperature. So the recovery creep is at the higher temperature range, and the creep rate here does not decreases rapidly as in the case of the lower temperatures. Then the third category is the diffusion creep. Beyond a particular temperature, that is the 0.7 TMK, that is at a very high temperature, the creep is primarily influenced by diffusion and load stress applied has a little effect. This type of creep is termed as diffusion creep or plastic creep. So we have seen the three types of creeps. One is at the lower range of temperature, the second one is at the higher temperature, and the third one, which is the diffusion creep, is at a very high temperature. And we are just seeing the influences depending on the temperature. Now let us study about the factors that affect the creep. The first one is the creep is much more affected by the grain size, that is the microstructure, and the previous strain history. So the three factors are the grain size, microstructure, and the previous strain history. For example, cold work, etc. And the creep is also extremely structure sensitive. That is, the major factor which will affect any creep will be its structure. And the structure obviously includes the grain size, its microstructure, and the previous strain status. Then the second one, that is the major factor in creep, is the grain size. Single crystals show a high creep resistance than a polycrystalline materials. The third one is the thermal stability of the microstructure of alloys and its resistance to oxidation at high temperatures is another important factor. An annealed specimen, for having higher thermal stabilities, is as far superior in its creep resistance to a quenched steel for its poor thermal stability. That is, the major factor after the structural microstructural factors is the thermal stability of that structure and alloys and its resistance towards the oxidation at higher temperature. The creep mechanisms of crystalline materials. The creep can be of three types, as we can see in the chart given below, the figure which is showing a chart. Let us describe that the creep is first divided, or which is due to the three reasons. First one is the creep which is related to dislocation. Second one is a creep related to diffusional, and the third is related to grain boundary sliding. Now the dislocation related creep is further divided into three parts. The dislocation can be cross-slip type, climb type, and the glide type. This is the Harper-Dawn creep. Then the diffusional one is again divided into four parts. First one is called as the cobble creep, which is grain boundary diffusion controlled. The second one is Nabarro herring creep, which is the lattice diffusion controlled. The third one is the dislocation core diffusion creep, where the diffusion rate through core of edge dislocation is more. And the fourth one is the interface reaction controlled diffusional flow. So these are the creep mechanisms of crystalline materials. Let us know what is a cross slip and dislocation climb. Cross slip. In the low temperature of creep, screw dislocations can cross slip by thermal activation and can give rise to plastic strain as a function of temperature. The next is dislocation climb. Edge dislocations piled up against an obstacle can climb to another slip plane and cause plastic deformation as a function of temperature in response to stress. Rate controlling step is the diffusion of vacancies. Now this is well described in the figure given below. There is a figure here given below which is showing the diffusional creep in the two types. The first one is the Nabarro herring creep at higher temperature due to the lattice diffusion. Second is the cobble creep at lower temperatures, which is due to the grain boundary diffusion. In response to the applied stress, vacancies preferentially move from surfaces or interfaces, that is the grain boundary of specimen, transverse to the stress axis to surfaces or interfaces parallel to the stress axis, which is causing elongation. This process, like dislocation creep, is controlled by the diffusion of vacancies, but diffusional does not require dislocations to operate. Here the figure given is showing the flow of vacancies. The next we are going to study is about the grain boundary sliding. At low temperatures, the grain boundaries are stronger than the crystal interior and impede the motion of dislocations. Being a higher energy region, the grain boundaries melt before the crystal interior. Above the equicohesive temperature, grain boundaries are weaker than grain and slide past one another to cause plastic deformation. Now let us discuss about the creep resistant materials. High operating temperatures gives better efficiency for a heat engine. Hence, there is a need to design materials which can withstand high temperatures. The figure given here shows the creep resistance leading to four things. The first one is high melting point, the example of which is ceramics. Second one is the dispersion hardening, that is TiO2 dispersed nickel. Third one is the solid solution strengthening. And the last one is the single crystal or aligned oriented grains. Cost, fabrication ease, density, etc. are other factors which determine the final choice of a material. The commonly used materials are iron, nickel, including the superalloys, and the cobalt-based alloys. Precipitation hardening instead of dispersion hardening is not a good method because as particles coarsen, that is the smaller particles dissolve and larger particles grow, that lead to the increase in the interparticle separation. Then the nickel-based superalloys have Ni3, Ti aluminum precipitates which form a low energy interface with the matrix, giving the low driving force for coarsening. Cold work cannot be used for increasing creep resistance as recrystallization can occur which will produce strain-free crystals. Also, fine grain size is not desirable for creep resistance because grain boundary sliding can cause creep elongation or cavitation. Further, single crystals, that is the single crystal titanium turbine blades in gas turbine engine have been used. Secondly, aligned or oriented polycrystals. So students, let's now study about the creep fracture. Creep fracture may take place at higher temperatures or longer stress times. So for a creep to fracture, it takes two factors. That is, first is the higher temperature or the second is the long duration stress times. For example, the creep fractures can be seen easily in ductile materials. Under moderate temperature and high stresses, it takes shorter times for a fracture to occur in creep. The nature of this type of fracture is exactly similar to that of ductile material, forming a neck before fracture. For a long time durations at low stresses, the fracture is similar to brittle fracture because of negligible deformation produced in the process. That is, we can see that we can divide the stress times into the higher stress times and higher temperature, then higher stress but the time shorter and moderate temperature, and the third one is long duration stresses which are low in magnitude, and depending on them the fractures are different types. That is, a fracture is similar to the ductile materials. In the first case, it is just similar in ductile materials. In the second case, when there is moderate temperature and high stresses, it is similar to ductile material, forming a neck. Then in the third case, where the long time durations are there but the magnitude of stress is low, then the fracture is similar to the brittle fracture. Metals sometimes fracture with very little plastic elongation at higher temperatures or after long periods of loading. Let us discuss the creep test. This test requires the measurement of 4 variables: stress, strain, temperature, and time. The objective of this testing is to determine the continuing change in the deformation of materials at elevated temperatures when stress is below the yield point. The aim of the creep test is to determine limiting creep stress. The figure given below shows the creep test in which there is a specimen, there is a platinum tube, platinum wire, then the electric furnace wall and the telescope, and the specimen is connected to the load. Stress rupture test. In the stress rupture test, Creep test is extended up to failure. One can calculate the following from this test. Number 1, time required to cause failure at a given stress and at constant temperature. Number 2, we can calculate minimum creep rate by measuring elongation as a function of time. The following graph is a graph between rupture time and stress. Here the rupture time and stress is plotted. The graph is mostly a straight line, but we can see some changes in the second and the third curve. The changes is due to the structural changes taking place in the material, that is due to recrystallization, grain growth, graphitization, oxidation, spherodation, etc. So students, let us summarize what we have learned in this module. This module describes about the creep. We have learned about the creep. Then we have seen the creep curve equations. Then we saw the types of creeps. Then we learned about the factors affecting the creeps. And depending on the different factors, we have the different types of creep. Then we learned in detail about the mechanism of creep. Then we learned the term creep fracture, and we saw the factors which affect the creep fracture or which leads to the creep fracture. Then we learned about the creep tests, among which we have learned about the stress rupture test. Then in the end, we see the applicability of the learned creep tests. So in short, this module gives you the detailed knowledge of creep, starting from the brief introduction, then the equations, then the types of creeps, then the factors which affects the creep, then the detailed mechanism of creep, creep fracture, then the tests of the creep, stress rupture test, and in the end, application of these creep tests. Thank you.